Okay, thanks, Piotr, for this very nice introduction. It's a pleasure for both of us to be here to join you in this monthly meeting of the Polish chapter of the Society of the Catholic Scientists. I will start this seminar, and after Father Gabriele will continue in the second part. And yes, my talk is divided in two parts. First, I will focus on how it's possible to see quantum gravity signal imprints in the early universe. A quick history of cosmology of the universe, and later I will focus on gravitational waves, prediction, discovery, and in particular primordial gravitational waves, which are really important for cosmology. And later I will speak about cosmic microwave background radiation, CMB, both temperature and polarization. But let's start with this slide. Probably you are familiar with this one slide history of our universe. You see on this axis time, not in linear scale, from the initial singularity to today, 13.8 billion of years after the singularity. And on the other scale, the scale factor that represents the expansion of the universe during his entire history. In order to describe this kind of expansion, we assume a universe which is isotropic and homogeneous, at least on large scales. So we can describe this expansion more or like this. And the parameter A describes the expansion of the universe. And you have an evolution of the scale factor of the universe. You see, the scale factor A is a function of time. And today we see, looking at the galaxy surface, this expansion of the universe, something which is described in the famous Hubble-Leibniz law. But today we will speak about expansion really at the beginning of the universe. You see this very, very quick expansion just after the beginning of the universe called inflation. And near this, in this very, very early times, in order to describe physics, you need to put together both gravity, general relativity, and quantum mechanics. And you can see that there is a time scale that you can build using the fundamental constants of gravity and quantum mechanics. So combining the gravitational constant, the Planck constant, and the speed of light, you come up with this time, which is called the Planck time. And when you are interested in the time scale of this magnitude, you need quantum gravity. And the problem is that we do not have a complete theory of quantum gravity. And so it's interesting to try to understand what we can understand on this epoch. You see there are quantum fluctuation at the beginning of the universe. You see in the cartoon. And there is after this very quick expansion, cosmic inflation. The universe underwent a phase of exponential expansion that sets up its very special initial conditions. And the quantum fluctuations during inflation turn out to play an important role. They give rise to the initial condition for the structure of the universe. You have these microscopic wavelengths of quantum fluctuation that is stretched by the enormous expansion of space and becomes a macroscopic fluctuation. And this is at the beginning of the cosmic structures that we observed today. And in order to explain this process, you need both quantum mechanics and general relativity. We are very close to this Planck scale that I tried to mention before. And the simplest model of inflation that we know predicts a stochastic background of gravitational waves. There is no astrophysical process that can produce such low frequencies gravitational waves. So what I'm going to speak to you today is to use the gravitation to study the gravitational background which was produced during this very quick expansion at the beginning of the universe, this inflation phase. Very close to the Planck scale. You see, the time scale is really, really small, 10 to the minus 38 seconds after the initial singularity. And in order to do this, we need gravitational waves. And what are gravitational waves? You know that more than 1 century ago, in 1915, Einstein published the papers of General Relativity. And the following year, he found that there was also a weak field solution of the equations that were gravitational waves. Gravitational waves were detected only 100 years later, the prediction of Einstein. You see there is this deformation of space-time, and were detected by the LIGO collaborations in 2015. Here you see a computer simulation of the gravitational waves from the merging of two black holes. And you see that the black hole's gravity stretches, curves space-times near them, and is a signal that is possible to observe today with special instruments. I will say something later. If you consider a plane, gravitational waves, probably you are more familiar to electromagnetic waves, but it's not so different. You have a plane wave, and the gravitational waves is a transverse wave, so the direction of distortion is perpendicular to the propagation direction. In this cartoon, the waves is propagating toward us. And you see that the gravitational waves does not change the total area of space, but it deforms space-times. And there are two kinds of polarizations called H plus and H cross. This is for a plane wave propagating in one direction. And like electromagnetic waves, you can construct a spectrum of gravitational waves. And the spectrum is extremely, extremely broad, the spectrum of gravitational waves. You see here the wave, the frequency, and the wavelength, and the period, yes. And it's extremely, extremely broad. And the frequency range of gravitational waves provides information about the source. So if you have a signal with very high frequency on the right side, the masses involved are not so big. Let's call them small, even if they are not so small. We are speaking about stars and supernovae. As if you consider lower frequencies, the masses are higher. And the detector size that you should use to probe these waves depends, of course, on the wavelength that you want to consider. So in this right region, for higher frequencies and smaller wavelengths, you can use this kind of detectors. And detectors which are Earth-based, like the LIGO, CAGRA, Virgo. Gravitational waves were discovered with this kind of detectors. You see the order of magnitude of this detector is of the order of kilometers. After there are multiple reflections, then you can have an effective length which is much bigger of the interferometer. But this is the order of magnitude of the instrument that you can build on Earth. If you are interested to gravitational waves with bigger wavelengths, you need to go to have a bigger interferometer. For example, there is this project to build an interferometer in space, LISA, Laser Interferometer Space Antenna. And here you see the wavelength, the distance between the detectors is the order of millions of kilometers. You can probe a different kind of physics. And even bigger scales are probed with pulsar. There is this project called Pulsar Timing Array, International Pulsar Timing Array, which is very interesting to probe a stochastic background of gravitational waves, for example, a background produced by supermassive black holes in our universe. And yes, so there are many, many different sources of gravitational waves at different energies. But there is no astrophysical process that generates very, very low big wavelength, also small frequencies of gravitational waves. And this is the region where we should look for primordial gravitational waves produced by inflation. And the idea in this case is to use the entire universe as a detector. So not to use other signals, to build an interferometer, to use pulsars, but to use the CMB, the cosmic microwave background radiation, to probe the primordial gravitational waves produced by inflation. Because it's not possible to go to such big scales with other techniques. So the idea is to use CMB. Let me say a few words about the cosmic microwave radiation that was produced when the universe cooled down at a temperature of the order of 3000 degrees, and the matter became neutral and allowed the light to propagate freely around in the universe, and CMB was generated. You see, much more later compared to the inflation scale. This happens when the universe had an age of order of 300,000 years, more or less. We are all familiar with the universe invisible light. This is a map, an all-sky map of the universe observed with the light that our eyes are able to see. But if we look at microwave wavelengths, the picture is very, very different. You see, this is an all-sky map of the universe observed at the microwave frequencies. The CMB was discovered, let's say, by chance, by two physicists, Penzias and Wilson. They were radio astronomers at the Bell Laboratories, and they found this signal, which was coming from every direction. They were pointing this very particular horn antenna for microwaves. And later, in Princeton, Dicke and other physicists were able to identify this radiation as something coming from the Big Bang. And the spectrum of this signal is almost a perfect black body with this temperature 2.725. And you see the error bars in this plot are increased of 4,000 in order to be able to see the error bars. It's almost it's the most perfect black body that we know. Penzias and Wilson won the Nobel Prize for these discoveries in 1978. And yes, for the discovery of the cosmic microwave background radiation. But that's not all the history, because there are also anisotropies in CMB. You see here there are spots on this map. If you look at the temperature, it's not exactly constant, but there are fluctuations, anisotropies, related to the quantum fluctuation that I explained you at the beginning. Stretched by inflation, this fluctuation growth, and here we can see the energies, the regions with the higher energies in blue, and the regions with lower energies in red. And the fluctuations are really, really small, but they are present, and they were detected by this satellite at the beginning of 1990s. And the PI of the satellite won the Nobel Prize in 2006. Mather and Smoot, they won the Nobel Prize for the discovery of the black body form of the CMB and for the anisotropies. Later, the research continued, of course, on this about CMB, WMAP, NASA launched the mission, and you see here the detail of the anisotropies can see with a much more details. And in the last decade, also ESA with Planck get a very nice map of the fluctuation of the anisotropies of cosmic microwave background. But we are not interested only to the temperature fluctuation, but also to polarization, because this electromagnetic wave, CMB, is also polarized. But let me see also if I can show you this movie about just to a quick summary about CMB. You can see from this movie how it's produced as a map of CMB. You have Earth, you look all around the universe, you produced an all-sky map. This is the visible light, what we can see with our eyes. You change frequency, you go to the infrared and microwave, and you increase the constant, and you can see the fluctuation. I think this is a nice animation made by ESA for Planck in order to explain more or less what is this plot that I show you. And as I was mentioning, it's important not only temperature is what we are seeing here, but also polarization. You see in this plot, there are not only blue and red spots, but there are also these small rods, black rods on the plot, which they describe the polarization. Because as any electromagnetic wave, also CMB is polarized. We all know that electromagnetic waves can be polarized. You see here in red an example of linearly polarized wave. You see the electromagnetic field is oscillating along a given direction during propagation, which is fixed. the light, for example, the light coming from the sun is not polarized, but after reflection, it becomes polarized. At least a certain amount of it, not all completely polarized, but you have a certain percentage of linear polarization after reflection. This is something we are familiar. If we look something reflected light with normal glasses or with Polaroid glasses, you see in this image, reflected light is removed, and so you can see better the street because the glasses are removing the light, the reflected light from which is reflected and which is polarized, and so it's removed by the filter, by the glasses. And something similar can be done with CMB. Also, CMB is polarized due to scattering of photons at last scattering surface. When CMB was generated, through Thomson scattering, you have a production of a certain amount of linear polarization due to Thomson scattering and to the quadruple anisotropy of the primordial fluctuations. And so it is possible. It's a very tiny signal, but it's possible to see also this pattern of CMB. This is the Planck map of polarization. And polarization is described in CMB using E and B modes, which is not related to E and B of electromagnetism. No, it's a different thing. They are not electric and magnetic field. But it's a way to describe this pattern. It's quite easy. You see, E modes are parity even. So if you reflect in a mirror, you see this blue pattern, E modes, does not change under reflection, under parity. Instead, B modes, we call them also curl-like modes, are parity odd. Under reflection, they change sign. So you decompose all this vector field using looking at E modes and B modes. And what is really interesting for us are these B modes, which are parity odd under reflection, because they can tell us something about the beginning of the universe, this inflation that I was mentioning before. I don't know, maybe someone of you remembers that this is what more or less what happens. You have the primordial gravitational waves produced by inflation that induce a certain degrees of B modes on CMB. So looking at CMB with the current experiment that we have and with future experiments, we are able to put constraints of the primordial gravitational wave background produced very, very close to the initial singularity. So it's a way to probe gravitational waves looking at CMB, because there is this effect on CMB. What the amplitude of this effect is described by this parameter R, which is called the tensor to scalar ratio. So all CMB experiments are trying to constrain this amplitude of the primordial gravitational waves on CMB. There was also a claim of the detection of B mode polarization on CMB, more or less, yes, exactly 10 years ago. There was a detection of a signal of the order of 0.2 of this parameter AR. By this collaboration, BICEP, there were also many newspapers speaking about it, but a few months later, they analyzed again the data and they discovered it was not really a signal, but it was something else. And they also wrote this book, Losing the Nobel Prize. In this case, there was no Nobel Prize. The problem is that in this, in order to be able to see this signal, you have to remove a lot of other signals coming in front of you, looking at the CMB. You have individual sources of stars, of galaxies, and you have to remove these sources. Later, you have to remove the radio emission from your own galaxy, from Milky Way. You have to remove the dust emission, always from the Milky Way, in order to be able to see the CMB. So it's quite a tricky process for temperature and even more difficult for polarization. So there is a big effort in this direction. There are also new experiments after Planck trying to put constraints. This is the proposal for a new mission, space mission for CMB called LIGHTBIRD, light satellite for the study of B-mode polarization and inflation from cosmic background radiation detection. And I do not think this plot is not so easy to understand, but you can understand that the signal that we are looking at is really, really small. This is the temperature of the CMB, and the signal of these B modes, primordial B modes, is, you see, several orders of magnitude smaller. And the error bars are still quite big in this region. So there is a big effort of the community try to say something on these modes, but there is still a lot of work on it. Anyway, it's an important technique to probe the evolution of the universe close to the beginning, close to the Planck scale, close to inflation. So this is a brief summary of what I tried to say you. This was a brief introduction of the current search for quantum gravity in the early universe, primordial gravitational waves, and how it's possible to study this signal looking at microwave polarization. And the detection of primordial B modes induced by primordial gravitational waves would bring us a glimpse of quantum gravity at work, very, very close to the initial singularity. And thanks for your attention. And now Father Gabriele will speak to us about quantum gravity.
Thank you very much for the invitation to talk on this Polish chapter, this seminar of the Polish chapter of Society of the Society of Polish Catholic Scientists. I will try to be as much clear as I can on this topic that it's quite, so to say, theoretical. It's less phenomenology, more theory, because it has to do with an attempt to formulate theories of quantum gravity, theories that try to quantize Einstein General Relativity. So the outline of this talk is a brief introduction to Einstein theory of general relativity, that is the theory we want to quantize. I will introduce the oldest approach to quantum gravity, is canonical quantum gravity Hamiltonian approach. I will talk briefly about the Hartle-Hawking solution of the Witt equation, since it was asked recently by Piotr something about science and theology. It's important to see how this solution essentially was inspired by some prejudices that the author, especially Hawking, had. I will talk about loop quantum gravity, string theory, and asymptotic safety approach to quantum gravity. That are the three main approaches on which I worked in quantum gravity. My research has been mainly quantum gravity, although now I am doing with Matteo something more on cosmology, and I will end with conclusion. As Matteo already highlighted, the 1915 was annus mirabilis for physics and cosmology, because Einstein wrote the Einstein equation of gravitational field. David Hilbert wrote the action of Einstein General Relativity, from which he derived also the Einstein equation, but from a mathematical point of view, in the paper, Einstein was more physical than mathematical. And Emmy Nader wrote the Nader theorem for conservation law. Well, Einstein General Relativity was, in 2015, we celebrated the 100 year of Einstein General Relativity. And you see also a famous drawn by this painter Escher, who tried to give a representation of what is really general relativity. I see in this the fact that there is no any preferred reference. Every direction is equivalent, but you can see other. Einstein General Relativity is an extension of special relativity. Deals with non-inertial reference frame, means two reference frames that are at non-constant velocity, one respect to the other, and is based essentially on what is called the equivalence principle. That is the gravitational mass, that is the mass through which two bodies attracts, is the same as the inertial mass. That is the quantity through which a body will oppose to motion. Gravitational effects are locally indistinguishable from acceleration effect. This is an important point. In fact, suppose that you are in a starship and this starship is accelerating, and you do an experiment, you drop an apple. The apple will, you see in your reference frame that the apple is attracted to the earth, to the ground, by an acceleration that is opposite to the acceleration of the starship. That is the same type of acceleration, strength, force you experience if you draw an apple and you have the starship on the earth. Since, you know, as you know, the attraction of the earth, the force is G. Now, in an empty space, an astronaut will experience no weight in a free-falling starship in empty space. If you have the same free-falling starship that is free-falling on the Earth, the astronaut in the starship will experience no gravitation in the reference frame of the starship, by the way, because the acceleration will cancel locally the gravitational effect. Now, geometry and gravity, this is an important point in Einstein General Relativity. Einstein interpreted the presence of gravitational field not as due to an actual force field, but to a space-time curvature. Now, so space-time curvature encodes what once was the force gravitational field. Inertial observers always move along the shortest line of space-time that are called geodesics. Measurement results deviates from what is predicted by Euclidean geometry due to the intrinsic space-time curvature caused, as I said before, by the presence of gravitational/energy, because energy or mass are equivalent in Einstein relativity. Relativity. The gravitational action, for example, of the sun on Earth is not a physical action on material bodies anymore, but but in the form of geometric modification of space. That means space-time is modified by the presence of massive body or energy, and so the gravitational force is encoded in the space-time structure and the curvature of space-time. Space-time modification induced by the presence of gravitational mass allow us to interpret gravitation geometrically, as we would say. All this is a consequence of the principle of equivalence. The geodesic structure and the metric structure of space-time coincide. Now, space-time in this way is a physical entity. It is a dynamical entity that is modified by the presence of the massive body, as well as energy. Massive body modifies, as I said also before in the previous slide, the space-time, and the space-time gains curvature. Free-falling body will move on the equivalent of straight line in curved space that are called geodesic. Gravitational force is not anymore an action of distance. It is a field theory like electromagnetism. And in particular, this field theory is now described completely by the space-time. Now, here you see what happens, as already Matteo shown, when two neutron stars, two stars collide. The gravitational field, that is the background thing you see, is modified by the fact that the mass concentration is modified, so it's produced gravitational waves, and these gravitational waves propagates on space-time and can be detected by LIGO, for example, as Matteo already explained. Now, as a corollary of the equivalence principle, we have the covariance principle. The laws of physics are the same, are covariant in every reference frame. That means in every reference frame now, even if two frames are accelerating, one respect to the other, you write the equation, Einstein equation, and the form of the equation is always the same in every reference frame. And all the physics should be covariant. You should be able to write all the same equation in every reference frame, also if this reference frame are accelerating one to respect to the other. This is completely new because some of you that in the past have studied, for example, elementary physics, you have noticed that in order to deal with what they were called non-inertial reference frame, you have to introduce what they are called inertial forces. Not anymore with Einstein General Relativity and with this principle of covariance. The equations are generally covariant. They are preserved in form under arbitrary. So this is the other point. The Einstein equations are invariant under arbitrary transformation of coordinates. This is also a new novelty. The only problem with this theory is that it has singularities, and in physics, singularity is always a great problem. I mean, Einstein General Relativity produces a solution that can be singular. There is the Big Bang singularity that already Father Matteo talked, and there is also the black hole singularities. There are also naked singularities. Einstein generally is full of singularities. And singularities in general, in physical law, is a signal that the physics breaks down. So in general, when there is a singularity, it's a signal you need a new physics. Now, already Father Matteo introduced what is a Planck temperature, because if you combine together what is the h bar, the gravitational constant, the velocity of light, you got some fundamental quantity that is called the Planck temperature, the Planck mass, the Planck time, the Planck length, the Planck energy, the Planck density, that are a signal that there is a fundamental unity, so to say, below which probably a new physics starts. This new physics anyway is unknown. But since at very small distance, we know that physics of atomic scale and subatomic scale in general obeys what are called quantum mechanics and quantum field theory. We think that at small scale, that is also at higher energy, the physics that will work should be a physics that joins Einstein General Relativity with quantum mechanics, and this is called quantum gravity. Now, Einstein General Relativity is in general considered a successful phenomenological theory at laboratory level, for the solar system, at galactic level, for distances that is bigger than what we have introduced, the Planck length. Singularity problem and quantum mechanical behavior of matter energy at small scale suggest that the quantum mechanical behavior of the gravitational field should work. This is called quantum gravity. At small distance, it means at high energy. There are many different approaches to quantum gravity. Probably you have heard the major approach. You have heard about string theory, loop quantum gravity. Less known are non-commutative geometry, causal dynamical triangulation, and asymptotic safety. General relativity, in general, is considered an effective theory, not a fundamental theory. Why? Because it has a coupling constant. This is important in quantum field theory. That has it's not dimensionless. It has a dimension of length to the -2 in natural unit. So this is a signal that the theory is not a fundamental theory, but it's an effective theory. So there should be some other theory that is more fundamental than Einstein General Relativity. This is quantum gravity, but this is still unknown. The most the most ancient, so to say, the oldest approach to quantum gravity is called canonical quantum gravity, and it is an old approach because the first approach was developed by Dirac, by DeWitt, and other very well-known physicists. Essentially, it's based on the fact that you quantize Einstein General Relativity writing an Hamiltonian theory. But in order to write an Hamiltonian theory, you have to suppose that space-time is a space that develops in time, because this is the only way in order to build a base on which to write an Hamiltonian theory. And in this Hamiltonian theory, this vision, you have a three-dimensional surface, the space that evolves in time. As I said, it's one of the oldest approach. It's based in what is called the ADM, by the name of the author who started this project, that is Arno with Esser-Missens. It's a three-dimensional space surface that evolve in time. The goal is to write an Hamiltonian density. This is more a technical term anyway, that is a function of the gravitational field. This can be done, and one arrives to what is called the equivalent of the Schrödinger equation in quantum mechanics. It is called the Wheeler-DeWitt equation. The Wheeler-DeWitt equation is a functional equation, so to say, in which you have to solve the unknown quantity is the wave function of the universe. No, you can write what is called the wave function of the universe that could give information about the universe when it was at below the Planck length, and like in quantum mechanics. Of course, there are many caveats on this because it's really the Wheeler-DeWitt equation is not very well defined. Nobody really never solved the Wheeler-DeWitt equation, but this is the only part on which I will talk about science and theology. there is this problem that is in the mind of many scientists, because the Big Bang, that is the singularity that we are trying to solve with quantum gravity, poses the problem of the beginning. Now, the beginning in the mind of many scientists is a problem. In fact, beginning is confused with creation. So if there is a beginning, you have to introduce a creator that started the beginning. And this creator is a God. So in order to avoid this idea of God, you have to eliminate the singularity. No, this is the Hawking-Hartle proposal. They solved not the Wheeler-DeWitt equation, but a simplified model of the Wheeler-DeWitt equation on a particular cosmological model that is the Friedmann-Delameter-Robertson-Walker solution. It is the same solution used to describe the universe on large scale. But if you impose this mini superspace on the Wheeler-DeWitt equation, you get a simple model that can be solved. But they introduced a trick. What is the trick? They say that below the Planck length, you have a shift from the Lorentzian geometry to the Euclidean geometry. Lorentzian geometry to a degree means that below the Planck length, you don't have anymore a singularity, but you have surfaces that are compact. So below the Planck length, you have surfaces like this that are sphere. A sphere does not have a particular point on each surface, while a cone has a particular point and gets a beginning. The sphere does not have a beginning, so every point is equivalent. So there is no beginning. And so the idea of Hartle and Hawking is that below the Planck length, you have this Euclidean phase, and there is no real time. The concept of time emerges in the transition from the Euclidean regime to the Lorentzian regime. In this way, they seem to have no need of a beginning. There is no beginning in the sub-Planckian regime. And the universe seems to emerge from nothing. And so, especially Hawking used to say that this model, physical model, has resolved the problem that before was introduced with the creatio ex nihilo, because they created a model in which essentially time emerged from a vacuum, a gravitational vacuum that was Euclidean, and so you don't need anymore the creation from nothing. But Hawking, in reasoning in this way, does the same mistake of the God of the gaps that was used also in the past, because singularity involves the problem of explaining for him the beginning, which is confused with the term creation that is theological. This seems to lead to the need of concept of God, a sort of demiurge that will create the energy matter of the universe from the beginning, and after will escape. This is a sort of deism, so to say. This is a philosophical mistake. Why? Because Descartes did the same mistake when he introduced his system. In order to be sure that there was no a devil that was making him wrong, you have to introduce the idea of a benevolent God that will say that what was introducing was right. But this is really a God of the game. A God that you introduce when you don't know really something and you need a God. But this is not really the Christian God and the God of a good theology. This is a God that of ignorance, I would like to say, the God of the games. Furthermore, Hawking is also ontologizing his model, because every scientific model, it's not definitive, because there are already some model, for example, that talks about the phase before the Big Bang. So if you introduce this kind of model and you say that it's definitive, you are also making a mistake. Anyway, after this digression about canonical quantum gravity, I will introduce another approach to quantum gravity that is called loop quantum gravity. That has been introduced by three actors, the three main scientists. The one was Abaya Steger, and two of his collaborators, Liz Molin and Carlo Rovelli. Loop quantum gravity essentially is a canonical approach to quantum gravity. So you always have the Wheeler-DeWitt equation, but you introduce what is called the spin network. That means a network of spin, representation in technical term of the SO2 group. And this idea of spin network was originally introduced by Penrose anyway. And you write some function on the spin network that are essentially, you write a curve, you write a functional on this curve that depends on the connection and of the Pauli matrix. Anyway, if you do in this way and you are able to write solution of the Wheeler-DeWitt equation. And in particular, you find that this solution will give as a result that the area is quantized, not the volume, the area is quantized in loop quantum gravity. In particular, you know, you have heard that Hawking, Beckstein and Hawking, they found that the black hole has an entropy associated with black hole that is proportional to the area. If the same formula can be derived by loop quantum gravity, and you find that if you write the entropy like the formula I wrote, K times the logarithm of the number of microstates of the spin network, you find that you get the same formula of Beckstein and Hawking. There is also another approach connected to loop quantum gravity that is spin forms. Since they have a technical problem for which a constraint, I mean, an equation that comes from their approach to gravity, cannot be, it's not closed. It's another, they have to solve in some sense this equation. They introduce a discrete approach that are spin network evolving discretely in time. And this is the new approach to loop quantum gravity that is called spin forms. Anyway, quantized general relativity, as we already said, is perturbatively normalizable. It is believed that it's an effective theory, as we already said, for length bigger than the Planck length, rather than a fundamental theory. In general, theories are fundamental if they are perturbatively normalizable. What this means? If the infinities of the theory at quantum level can be absorbed by redefinition some parameter, like the mass, the energy, etc. A theory is perturbatively non-normalizable if we have to introduce a number of counterterms with a parameter, and the number of counterterms is infinite, so to say. So in general, to be normalized, the number of counterterms should be finite. If the number of counterterms increases as a series, it's infinity, the theory is not anymore predictive, and so the theory is not normalized, it's an effective theory. This is what happens with gravity if you try to quantize with the technique of quantum field theory. Now, string theory. Gabriele Veneziano in 1968 introduced a model for strong interaction in which introduced a function that was dual in the S and T channel. These are technical terms. And this was it's considered the beginning of string theory, because later other people like Nielsen, Ambo, Susskind, they used the Veneziano formula, and they say that in the strong interaction, two quarks were linked by a string a flux of energy. And they start to use strings to model strong interaction. But in this model, that was a quantum model, they found in the spectrum, they found that the theory made sense only in 26 dimensions. Okay, but there was also states with that were particles with negative energy that are called tachyons that made the theory unstable. And there were also some unknown spin 2 states that were not able to understand. Later, they were identified like gravitons, that are the particle, the quantum particle that should come from quantization of Einstein General Relativity. Later, anyway, this model of strong interaction was abandoned because the gauge theory were introduced and they worked better than this model coming from Veneziano ambit. Now, string theory, but later this string theory was, so to say, resuscitated because this spin 2 particle was interpreted as gravitons. And string theory is a theory in which, at the fundamental level, you have not anymore point particle, but we have a more fundamental object is called string that could be open or closed. And the action of a string is, for those who are familiar with this, with Lagrangian, so to say, the action has this form that are an object that is it's a two-dimensional surface immersed, embedded in a higher dimension. And this is the action of string theory in the Polyakov approach. And once you write the string theory in the classical level, you can quantize bosonic string theory. You expand the field in Fourier series, and you write this series as harmonic oscillator. There are two kinds of string, open and closed. Open string corresponds to gauge theories. Closed string correspond to gravity. And in this way, you quantized gravity, quantizing all the fundamental interaction, because all the fundamental interaction we know comes out from as a first excited level of string theory. So you have closed string that correspond to spin 2 massless state and correspond to the gravitons. And the other particles that we know comes from open string. But in order, this theory technically has some problem, because it makes sense only in 26 dimensions. Otherwise, we have an anomaly that is called the conformal anomaly. The presence of tachyons, anyway, makes string theory unstable. It's unstable in theory. So this is in general what happens. In general, in physics, you have what are called Feynman diagrams for particle. Now, for string, we have the equivalent of Feynman diagram that are interaction of strings, closed string, open strings, and interaction of open and closed string. And the advantage of string theory is one, that in order to quantize gravity, you have to, so to say, unify all fundamental force in one object that is called the strings. The string is an object that is more fundamental than the particle. And the advantage, they say, of string theory is that you don't have anymore the problem of infinities in quantum field theory, because ultraviolet infinities are cured by string theory. Anyway, bosonic string theory, as I said, is unstable because of tachyons. It's possible to introduce a new string theory for that goes beyond the bosonic string theory, because to each bosonic degree of freedom, introduce a fermionic degree of freedom, so you have what are called superstring. So if you introduce in string theory supersymmetry, you get superstrings. Superstrings make sense in 9 + 1 dimension, always with this issue of conformal unknown. And there are 5 in a non-equivalent superstring theory that should be unified by theory that is called M theory, but this is also speculation. One important thing anymore that is in string theory, they were able to reproduce the Bekenstein-Hawking formula for black hole entropy into quantum regime. Now, another approach that is not very well known, but it's also important, it's asymptotic safety approach to, I am almost at the end, to quantum gravity, because the asymptotic safety approach to quantum gravity is based mainly on the conjecture by a famous physicist that recently died, Weinberg, in 1979. He said that in non-normalizable theory, one technique is to put a cutoff. I mean, you don't integrate all over energy. You put a cutoff on the energies, and you write the coupling constant as function of the cutoff. So what the next step is to send to infinity the cutoff and search for a non-Gaussian fixed point in the space of the parameter. If you find this non-Gaussian fixed point, you quantize the theory, in this case quantum gravity, the non-Gaussian fixed point. He proved that in 2 + epsilon dimension, this approach works. In 4 dimensions, recently in 2002, Reuter and Sauressig proved that it works also for gravity. So this means that there is a way to quantize gravity, not in a perturbative way, but what is called in a non-perturbative way. And this approach is essentially the same approach that was introduced by Kenneth Wilson, that is a physicist who got also Nobel Prize, for the study of statistical mechanics, essentially. And so the idea is to construct by performing an infinite cutoff limit, to construct the theory at they construct by performing the infinite cutoff limit a non-Gaussian fixed point, and you define the theory at a non-Gaussian fixed point. So you have to find this non-Gaussian fixed point in the space of the parameter and define the theory, as I said before, at the non-Gaussian fixed point. In general, what happens, there are directions that are divergent, and that's the reason for which the theory is divergent, etc. I show here. So you eliminate this divergent direction, and you concentrate only on the convergent direction. Now, this is more technical. Essentially, there is a mathematical way to work in this direction. You have to write an effective average action in asymptotic safety. The F-state average action contains all the modes for P. You have to put a cutoff. This effective average action contains all the modes for P bigger than the cutoff, and not yet modes for P less than K. The effective average action should provide the dependence of K from the fundamental. So the cutoff should depend from the fundamental constant. And in general, you can do this procedure not, with precisely. You have to do what is called a truncation. And there are technical problems. Anyway, it has been proved that this method works. So there is a way to quantize in non-perturbative way, not in perturbative way, Einstein General Relativity, and to write what is called Quantum Einstein General Relativity with this procedure. It is quite complicated. So I will end up with conclusion. A well-established theory of quantum gravity, unfortunately, does not exist yet. One of the problems is lack of experimental tests. Matteo has shown that probably in the future there will be some hope that some imprints of quantum gravity can be detected in CMB. We have analyzed three fundamental approaches to quantum gravity. Okay, four really, I forgot one. One is canonical quantum gravity. That is the oldest approach. A new version of canonical quantum gravity is loop quantum gravity that has mathematical problem. String theory that is on drawbacks because, as you probably know, supersymmetry has not been found yet, and all experiments that say has not detected any supersymmetry. The third approach I introduced is asymptotic safety. It's quite young, dates back to the, as I shown to Weinberg in 1979, later Reuter, but it's based on this search for non-Gaussian fixed point. But this non-Gaussian fixed point has been reached not precisely by doing what is called a truncation, but people have shown that performing more and more precise calculation, there is always a fixed point. So there is an hope that Einstein General Relativity could be quantized in a perturbative way. More work appears to be needed to find the right theory of quantum gravity. One way of proceedings is to compare the result, as it has been done in the case of black hole entropy of Einstein of quantum gravity with Einstein General Relativity in the case in which when you do what is called the classical limit, you send h bar to 0, and you can confront the result you have with your theory of quantum gravity with classical result. That's it.